When people hear that atoms are mostly empty space, it often sounds shocking, even unbelievable. After all, everything around us feels solid and real. A table resists your hand, the ground supports your weight, and walls stop you from walking through them. Yet modern physics tells us that if you zoom in far enough, matter is not packed solidly like bricks in a wall. Instead, it is made of tiny atoms with vast regions of space between their parts. But calling this space nothing is deeply misleading. As Richard Feynman emphasized, the emptiness inside atoms is not truly empty at all. To understand this, we first need to look at what an atom actually is. An atom consists of a very small, dense nucleus made of protons and neutrons, surrounded by electrons. The nucleus contains almost all the mass of the atom, but it occupies an incredibly tiny volume. The electrons are much lighter and are spread out in regions around the nucleus. The distance between the nucleus and the electrons is enormous compared to the size of the nucleus itself. This is why physicists say atoms are mostly empty space. However, empty here does not mean the same thing as an empty box or a vacuum in everyday life. In classical thinking, empty space is just nothingness, no matter, no activity, no influence. But physics, especially quantum physics, shows us that space itself has structure and properties. Even where there are no particles, there are fields, energy, and constant activity. One of the most important things filling the space between atoms is electromagnetic fields. Atoms are made of charged particles, positively charged protons, and negatively charged electrons. These charges create electric fields that extend throughout space. When two atoms come close to each other, their electric fields interact. These interactions are what prevent atoms from passing through one another. When you press your hand against a table, you are not touching solid matter in the usual sense. Instead, the electric fields of the atoms in your hand repel the electric fields of the atoms in the table. This repulsion creates the sensation of solidity. So what feels like solid contact is actually an interaction of fields across empty space. Feynman loved to point out this counterintuitive truth. He explained that the firmness of matter does not come from tiny hard balls packed together, but from forces acting across space. The space between atoms is filled with these forces, constantly pushing and pulling, maintaining the structure of matter. Without these invisible interactions, matter as we know it could not exist. Beyond electromagnetic fields, quantum physics adds another layer of meaning to empty space. In quantum field theory, which Feynman helped develop, particles are not just little objects moving through empty space. Instead, every type of particle is associated with a field that exists everywhere in the universe. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field, and so on. This means that even in regions where there are no particles, the fields themselves are still present. These fields are never completely calm. Due to the uncertainty principle, they are always fluctuating. Energy briefly appears and disappears, giving rise to what physicists call virtual particles. These particles pop into existence for extremely short times and then vanish again, but their effects can be measured. Experiments like the Casimir effect show that empty space can exert measurable forces, proving that it is not truly nothing. So when we say atoms are mostly empty space, we are really saying they are mostly filled with fields and potential activity rather than solid matter. This emptiness is more like a restless ocean than a quiet void. It is structured, dynamic, and full of influence. Another important idea is that electrons do not orbit the nucleus like planets orbit the Sun, even though that picture is often used in simple explanations. In reality, electrons exist in quantum states described by probability waves. These waves spread out over space, meaning the electron is not a tiny dot at a precise location, but a cloud of probability. The space inside an atom is shaped by these quantum wave patterns, which determine how atoms bond, how molecules form, and how chemistry works. Again, this shows that the space is organized and meaningful, not empty in a trivial sense. Feynman also emphasized that our everyday intuition about emptiness comes from humans, scale experiences, not from the microscopic world. At our scale, empty space usually means air or a vacuum with very little matter. But at the atomic scale, the rules are different. Space is governed by quantum laws, fields, and probabilities. What seems like nothing is actually the foundation of everything. This understanding changes how we think about reality. It tells us that matter is not the primary substance of the universe in the way people once believed. Instead, interactions, fields, and energy play a more fundamental role. The solidity of objects, the stability of atoms, and even the existence of light all depend on what happens in this so-called empty space. In a deeper sense, the idea that atoms are mostly empty space challenges our assumptions about what is real. If solid objects are mostly space, and that space is filled with invisible fields and forces, then reality is far more subtle than it appears. Feynman found this both humbling and exciting. He believed that recognizing how strange and beautiful the universe truly is was one of the great joys of science. So, atoms are mostly empty space, but not truly nothing. The space within and between atoms is alive with electric fields, quantum fluctuations, probability waves, and constant interactions. It is this hidden activity that gives matter its structure and strength. What we call emptiness is, in fact, the stage on which the deepest laws of nature play out. Electric fields fill the space between charged particles, and this idea is one of the most important concepts in modern physics. It explains how objects can influence one another without touching, how atoms hold together, and why the world feels solid even though it is mostly empty space. Although electric fields are invisible, their effects shape nearly everything we experience in everyday life. To understand this idea, we first need to think about electric charge. Certain particles, such as electrons and protons, carry electric charge. Electrons have negative charge, while protons have positive charge. Charges interact with one another, like charges repel, and opposite charges attract. But a key question arises: how does one charged particle know that another charge is nearby? How does the force travel across empty space? In early physics, forces were often imagined as acting directly at a distance, almost magically, but this explanation felt unsatisfactory. Over time, scientists realized that space itself plays an active role. A charged particle does not simply pull or push another particle directly. Instead, it creates an electric field in the space around it. This field extends outward in all directions and exists whether or not another charge is present. When a second charged particle enters this field, it experiences a force. In this way, the interaction happens locally, through the field that fills the space between them. An electric field can be thought of as a condition of space caused by the presence of charge. Wherever there is charge, the surrounding space is altered. If you were to place a tiny test charge somewhere in that space, the electric field at that point would determine how strongly and in which direction the test charge would be pushed or pulled. This means the space between charged particles is not passive or empty. It is active and structured by the field. This concept becomes especially important when we look at matter on the atomic scale. Atoms are made of positively charged nuclei and negatively charged electrons. The electrons are not glued to the nucleus, nor are they connected by tiny physical strings. Instead, they are held in place by electric attraction. The electric field created by the nucleus fills the space around it, and the electrons exist and move within this field. The structure of the atom is therefore determined by electric fields shaping the behavior of charged particles. Electric fields also explain why atoms and objects do not collapse into one another. When two atoms approach closely, the electrons in one atom feel the electric fields of the electrons and nuclei in the other atom. Because electrons have the same negative charge, their electric fields cause repulsion. This repulsion becomes very strong at short distances and prevents atoms from overlapping. When you press your hand against a table, the sensation of hardness is not caused by solid matter touching solid matter. It is caused by electric fields in your hand pushing back against electric fields in the table. The space between atoms is doing all the work. Richard Feynman often emphasized this point because it challenges common sense. We imagine solidity as something fundamental, but in reality, it emerges from electric forces acting across space. The electric field is the medium through which these forces operate. Without it, matter would have no structure, no stability, and no resistance. Electric fields are not limited to atoms. They exist on all scales. A charged balloon can stick to a wall because the electric field of the balloon rearranges charges in the wall, creating attraction. Lightning occurs when strong electric fields build up between clouds and the ground, eventually becoming powerful enough to move charges through the air. Every electronic device, from a smartphone to a computer, relies on carefully controlled electric fields to move electrons and process information. Another important feature of electric fields is that they store energy. The energy is not located inside the charged particles themselves, but in the field spread throughout space. When charges move or when fields change, energy flows through space. This idea leads naturally to the concept of electromagnetic waves, such as light, which are oscillations of electric and magnetic fields traveling through space. Even in a vacuum, light can propagate because electric and magnetic fields do not need matter to exist. They need only space. In modern physics, especially in quantum field theory, electric fields are understood in an even deeper way. The electromagnetic field is considered a fundamental entity that exists everywhere in the universe. Charged particles are sources of this field, but the field itself has its own reality. It can fluctuate, carry energy, and interact with other fields. This means that the space between charged particles is filled not just with abstract mathematical ideas, but with something physically real. This understanding changes how we think about empty space. What seems like emptiness is actually full of invisible structure. Electric fields give space properties that affect how particles move and how matter behaves. Space is not just a stage on which physics happens. It is an active participant. Electric fields also help explain why interactions are not instantaneous. Changes in a charge or its motion do not affect distant charges immediately. Instead, changes in the electric field propagate through space at a finite speed, which is the speed of light. This ensures that cause and effect remain consistent with the laws of relativity. Again, the field is central. It is the messenger that carries influence from one place to another. In the end, saying that electric fields fill the space between charged particles is not just a technical detail. It is a profound statement about the nature of reality. It tells us that forces are not mysterious actions across nothingness, but results of fields that exist throughout space. These fields shape atoms, build matter, transmit energy, and create the physical world we experience. What appears to be empty space is actually rich with electric activity. The stability of atoms, the solidity of objects, and the flow of energy all depend on electric fields silently filling the gaps between charged particles. Far from being nothing, this space is one of the most important ingredients of the universe. The idea that quantum fields exist everywhere, even in a vacuum, is one of the most profound discoveries of modern physics. It completely changes how we think about empty space. In everyday language, a vacuum means nothing there, a region without matter or air. But in quantum physics, a vacuum is not truly empty. Instead, it is filled with invisible entities called quantum fields, and these fields form the deepest foundation of reality. To understand this, it helps to move beyond the idea that the universe is built primarily from tiny particles. Classical physics encouraged that picture. Matter was made of solid particles, and space was just an empty container where things happened. Quantum physics replaces this view with a much stranger and richer one. According to quantum field theory, the most fundamental ingredients of nature are not particles, but fields. Particles are simply small vibrations or excitations of these fields. A quantum field is something that exists at every point in space and time. There is an electron field everywhere, a quark field everywhere, and an electromagnetic field everywhere. Even if there are no electrons present in a particular region of space, the electron field is still there. It is like an ocean that exists everywhere, even when there are no visible waves on its surface. An electron appears when the electron field is excited, just as a wave appears when water is disturbed. This means that empty space is never truly empty. Even in the most perfect vacuum imaginable, where all particles have been removed, the fields remain. They cannot be turned off or removed because they are part of the structure of the universe itself. Space and quantum fields are inseparable. One of the most surprising consequences of this idea is that these fields are never completely still. Due to the uncertainty principle, a fundamental rule of quantum mechanics, the energy of a field cannot be exactly zero everywhere. As a result, quantum fields constantly fluctuate, even in a vacuum. Tiny amounts of energy briefly appear and disappear. These fluctuations are not just theoretical ideas. They have real, measurable effects. Physicists often describe these fluctuations in terms of virtual particles. Virtual particles are temporary excitations of quantum fields that pop into existence for extremely short times and then vanish again. They cannot be directly observed like ordinary particles, but their effects can be measured. For example, they contribute to forces between particles and cause subtle shifts in energy levels inside atoms. This shows that the vacuum is active, dynamic, and full of invisible processes. One famous demonstration of this activity is the Casimir effect. When two uncharged metal plates are placed very close together in a vacuum, they experience a tiny attractive force. This force cannot be explained by classical physics. It arises because quantum fields behave differently in the small gap between the plates than they do in the surrounding space. The vacuum itself is exerting a force, proving that it is not nothing. quantum fields existing everywhere also explain why particles behave the way they do. Take the electron as an example. An electron is not a tiny solid dot moving through empty space. It is an excitation of the electron field. When the field vibrates in a certain way, we observe that vibration as a particle with a specific mass and charge. This view helps explain why all electrons are identical. They are not separate objects with individual histories. They are all manifestations of the same underlying field. Richard Feynman played a major role in developing and explaining these ideas. He emphasized that what we call particles are simply convenient ways of describing how fields interact. In his view, the vacuum is not a background of nothingness, but a complex state of lowest possible energy filled with potential. The apparent emptiness of space hides an enormous amount of structure. This understanding also reshapes how we think about forces. Forces such as electromagnetism arise from interactions between quantum fields. When charged particles interact, they are really exchanging energy through the electromagnetic field. Even when no particles are present, the field itself still exists and can carry energy in the form of light or other radiation. This is why light can travel through empty space without needing a material medium. Another important implication is that space itself has physical properties. Because quantum fields fill space, space can store energy, transmit influences, and respond to changes. It is no longer just a passive stage where physics happens. It is an active participant. Changes in fields propagate through space at finite speeds, respecting the laws of relativity. This makes the universe more interconnected than classical physics ever imagined. The idea that the vacuum is full of quantum fields also has deep connections to cosmology. The energy of the vacuum may play a role in the expansion of the universe. Some theories suggest that vacuum energy contributes to dark energy, the mysterious force driving the accelerated expansion of space. Once again, what appears to be empty turns out to be crucial on the largest scales imaginable. On a philosophical level, this concept challenges our intuition about nothingness. Human experience teaches us that nothing means absence. But physics reveals that absence of matter does not mean absence of reality. Even where there are no particles, the laws of nature are still present, embodied in quantum fields that never disappear. In summary, quantum fields exist everywhere, even in a vacuum, because they are the fundamental building blocks of the universe. Particles are temporary excitations of these ever-present fields. The vacuum is not empty, silent, or inactive. It is alive with fluctuations, energy, and potential. This invisible activity shapes matter, transmits forces, and may even influence the fate of the universe itself. What we once called empty space is, in truth, one of the richest and most fascinating aspects of reality. The idea that virtual particles constantly appear and disappear is one of the strangest and most fascinating results of modern physics. It challenges our everyday understanding of reality and forces us to rethink what empty space really means. At first, this idea sounds almost mystical, as if particles are popping out of nothing and vanishing without reason. But in physics, virtual particles are not magic or fantasy. They arise naturally from the laws of quantum mechanics and play a crucial role in how forces work and how the universe behaves at its most fundamental level. To understand virtual particles, we must first understand that the quantum world does not behave like the world we experience directly. In everyday life, objects have clear positions, energies, and lifetimes. A ball exists, it moves, and it does not suddenly vanish into nothing. But in the quantum realm, nature follows different rules. One of the most important of these rules is the uncertainty principle, which limits how precisely certain properties can be known at the same time. Among these limits is a deep connection between energy and time. According to quantum mechanics, energy does not have to be perfectly fixed for extremely short periods of time. For very brief moments, small amounts of energy can fluctuate without violating the laws of physics. These temporary fluctuations allow quantum fields to briefly create excitations that look like particles. These short-lived excitations are what physicists call virtual particles. They are not particles in the usual sense, but temporary disturbances in quantum fields that appear and disappear too quickly to be directly observed. Virtual particles are different from real particles. Real particles, like electrons or photons of light, can be detected by instruments and can exist for long periods of time. Virtual particles, on the other hand, exist only during interactions. They cannot be isolated, measured directly, or stored. Their existence is inferred from their effects, not from direct observation. Even though they are virtual, their consequences are very real. One of the clearest examples of virtual particles at work is the force between charged particles. When two electrons repel each other, classical physics might say they push each other through empty space. Quantum field theory gives a deeper explanation. The electrons interact by exchanging virtual photons, which are temporary excitations of the electromagnetic field. These virtual photons carry energy and momentum between the electrons, producing the force we observe. The electrons never touch, but the constant exchange of virtual particles makes the interaction possible. This idea applies to all fundamental forces. The attraction between protons and neutrons inside an atomic nucleus is explained by the exchange of virtual particles associated with the strong force. Even gravity, in theoretical descriptions, is often discussed in terms of virtual particles, although gravity is not yet fully understood at the quantum level. In every case, virtual particles act as messengers, allowing forces to operate across space. Virtual particles also appear even when no obvious interaction is happening. In what we call a vacuum, quantum fields are still present everywhere. These fields cannot remain completely calm. They constantly fluctuate, producing brief appearances of virtual particle-antiparticle pairs. These pairs emerge, exist for a tiny fraction of a second, and then annihilate each other, returning their energy to the field. This constant activity means that empty space is actually full of microscopic motion. Although virtual particles exist only fleetingly, their effects can be measured. One famous example is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, they experience a small attractive force. This force arises because virtual particles behave differently in the narrow gap between the plates than they do in open space. The result is a pressure that pushes the plates together. This experiment shows that virtual particles are not just mathematical tricks. They influence the physical world in measurable ways. Another example comes from the behavior of electrons in atoms. Virtual particles slightly modify the electric field around the nucleus, causing small shifts in the energy levels of electrons. These shifts have been measured with great precision and match the predictions of quantum theory. Without virtual particles, these subtle effects would not exist. Richard Feynman played a key role in helping physicists understand and calculate the effects of virtual particles. His famous diagrams provide a visual way to represent interactions between particles, showing how virtual particles are exchanged during these processes. Feynman emphasized that these diagrams are not literal pictures of particles traveling through space, but powerful tools for calculating probabilities. Still, they capture an essential truth. Interactions in the quantum world involve constant creation and annihilation of temporary excitations. It is important to avoid misunderstanding what virtual particles are. They do not violate conservation laws in a careless way. Over longer timescales, energy and momentum are conserved exactly. The temporary fluctuations allowed by quantum mechanics are tightly constrained and disappear almost instantly. Virtual particles do not pop into existence and roam freely. They are confined to interactions and fleeting moments. The idea that virtual particles constantly appear and disappear also has deep philosophical implications. It tells us that nothingness is not stable. Even when all matter and radiation are removed, the laws of quantum physics ensure that activity remains. The vacuum is not a dead void, but a dynamic background filled with potential and motion. This challenges the classical idea that the universe is made of solid objects moving through empty space. In a deeper sense, virtual particles reveal that reality at its core is probabilistic and restless. The universe is not built from static pieces, but from fields that are always fluctuating. Matter, forces, and even empty space itself emerge from this constant quantum activity. In conclusion, virtual particles constantly appear and disappear because quantum fields cannot remain perfectly still. These fleeting excitations enable forces, influence the behavior of atoms, and give structure to what we once thought was empty space. Though they cannot be seen directly, their effects are everywhere. Virtual particles remind us that the universe is far more active, subtle, and mysterious than our everyday experience suggests. The idea that forces, not solid matter, create stability is one of the most important insights of modern physics. It overturns the everyday belief that objects are stable because they are made of hard, solid stuff packed tightly together. When we touch a wall, sit on a chair, or hold a book, it feels as if solidity itself is doing the work. But when physics looks deeply into the structure of matter, it reveals something surprising. Stability comes from interactions and forces acting through space, hidden not from tiny solid blocks locked together. At the most basic level, all ordinary matter is made of atoms. Atoms themselves are not solid in the way we imagine. Each atom has a tiny nucleus surrounded by electrons, with vast distances between them compared to their sizes. If solidity depended only on matter being physically packed with no gaps, atoms would not be stable at all. They would collapse or pass through one another. The fact that they do not tells us that something else must be responsible. That something else is force. The primary force responsible for the structure and stability of matter at everyday scales is the electromagnetic force. Protons and electrons carry electric charge, and electric charges interact through electric fields. These interactions determine how atoms form, how molecules bind, and how large objects maintain their shape. The electrons in atoms are held in place by the attractive electric force between their negative charge and the positive charge of the nucleus. Without this force, atoms would simply fall apart. Stability also depends on repulsion as much as attraction. When two atoms approach one another closely, the electrons in one atom feel the electric fields of the electrons in the other. Because, like charges repel, a strong repulsive force arises at short distances. This repulsion prevents atoms from occupying the same space. It is this force that makes objects resist compression and gives us the sensation of hardness. When you push against a table, your hand does not collide with solid matter in a mechanical sense. Instead, the electric forces between the atoms in your hand and the atoms in the table push back against each other. This reveals a deep truth. The stability of everyday objects is not due to solid contact, but due to a balance of forces. Attraction holds structures together, while repulsion prevents collapse. Matter exists in stable forms because these forces reach equilibrium, not because matter is inherently rigid. On a deeper level, quantum mechanics strengthens this picture. Electrons are not tiny solid particles orbiting a nucleus like planets. They are described by probability waves, and their behavior is governed by quantum rules. One of these rules, often called the exclusion principle, prevents electrons from occupying the same quantum state. This principle adds another layer of stability to matter. It ensures that electrons arrange themselves in distinct layers around the nucleus, and that atoms maintain their size and structure. Again, stability arises from rules and interactions, not from solidity. Even within the atomic nucleus, stability is created by forces rather than solid components. Protons in the nucleus all carry positive charge and strongly repel one another. If electromagnetic repulsion were the only force at work, the nucleus would fly apart. What holds it together is another force, often called the strong nuclear force. This force acts at extremely short distances and overcomes the electric repulsion between protons, binding protons and neutrons together into a stable nucleus. Here, too, balance is everything. If the strong force were slightly weaker or stronger, stable atoms might not exist at all. At larger scales, forces continue to dominate. The shapes of molecules are determined by how electric forces balance between electrons and nuclei. Chemical bonds are not tiny hooks or glue, like substances. They are stable arrangements created by shared electric interactions. The rigidity of a crystal, the flexibility of plastic, and the strength of steel all arise from how forces act between atoms in different arrangements. Change the forces or their balance, and the material's properties change. Gravity, although much weaker than electromagnetism, also plays a role in stability at larger scales. Planets orbit stars not because space is filled with solid supports, but because gravitational attraction balances motion. Stars themselves are stable because gravitational collapse is balanced by pressure generated from nuclear reactions in their cores. On every scale, stability is the result of opposing influences reaching equilibrium. This force-based view of stability was emphasized by physicists like Richard Feynman, who pointed out that the feeling of solidity is an illusion created by interactions. He explained that what we experience as solid matter is really a network of forces acting across mostly empty space. The atoms in your body and the atoms in the ground never actually touch. Instead, they communicate through fields and forces that resist further compression. Understanding stability in this way changes how we think about reality. It shows that matter is not a collection of tiny solid objects stacked together, but a dynamic system held together by invisible interactions. Stability is not passive, it is active. Forces are constantly at work, balancing, pushing, pulling, and adjusting to maintain structure. This perspective also highlights how delicate the universe is. The stability we take for granted depends on precise values of fundamental forces. Small changes in these forces could make atoms unstable, prevent molecules from forming, or eliminate the possibility of complex structures altogether. The fact that matter is stable enough to form planets, life, and conscious beings is deeply connected to how these forces behave. In conclusion, forces, not solid matter, create stability because matter itself is mostly empty space. What holds the universe together is a complex web of interactions governed by fundamental forces and quantum rules. The firmness of objects, the shape of atoms, and the endurance of structures all arise from balances between attraction and repulsion. Stability is not built from solidity, but from the continuous, invisible work of forces shaping the world at every scale. Richard Feynman's view connects emptiness with activity in a way that completely reshapes how we understand reality. To most people, empty space suggests nothingness, no matter, no motion, no influence. It feels passive and inactive. But Feynman, drawing from quantum mechanics and quantum field theory, showed that this idea is deeply misleading. In modern physics, emptiness is not the absence of activity. It is one of the most active and essential components of the universe. Feynman often emphasized that our everyday intuition fails when we try to understand nature at very small scales. At the human level, emptiness usually means air or a vacuum with very little in it. But when physics examines space at the atomic and subatomic level, it finds that space is not an inert background. Instead, it is filled with fields, fluctuations, and interactions. What looks empty is actually busy with invisible processes that make matter and forces possible. One of the central ideas behind Feynman's view is that particles are not the fundamental building blocks of reality. In quantum field theory, which Feynman helped develop and explain, fields come first. These fields exist everywhere in space, even where no particles are present. Particles appear only when these fields are excited. From this perspective, emptiness does not mean the absence of reality. It means the fields are in their low, astenergy state. Even then, they are not completely still. According to quantum mechanics, fields can never be perfectly calm. The uncertainty principle ensures that there is always some degree of fluctuation. Energy briefly appears and disappears, creating temporary disturbances in these fields. These disturbances are often described as virtual particles. They are not particles in the ordinary sense, but they represent real activity happening in what we call empty space. Feynman used these ideas to show that the vacuum is dynamic rather than static. This connection between emptiness and activity becomes especially clear in how forces work. In classical thinking, forces like electricity or magnetism act across empty space as if by magic. Feynman rejected this picture. He explained that forces arise from interactions mediated by fields and their fluctuations. When two charged particles repel or attract each other, they are not reaching across nothingness. Instead, they are interacting through an active electromagnetic field that fills the space between them. Even when no particles are present, the field itself still exists and can influence events. Feynman's diagrams, which became famous tools in physics, visually represent this constant activity. They show particles interacting by exchanging virtual particles through space. Although Feynman cautioned that these diagrams should not be taken as literal pictures, they capture a deep truth. Interactions are processes happening within space, not across emptiness. Space is not silent, it is constantly involved. Another important aspect of Feynman's view is how it explains the solidity of matter. Atoms are mostly empty space, yet objects feel solid and stable. Feynman pointed out that this solidity comes from forces acting across that emptiness. When you press your hand against a table, the atoms in your hand do not collide with solid atoms in the table. Instead, electric forces between electrons push back, creating resistance. The empty space between atoms is where this interaction happens. Without the active role of space and fields, matter would have no stability at all. Feynman also connected emptiness with activity through his explanation of light. Light can travel through a vacuum, unlike sound, which needs air. This is because light is not a vibration of matter, but a vibration of the electromagnetic field itself. The fact that light can move through empty space shows that space is not nothing. It has physical properties that allow energy and information to propagate. Emptiness, in this sense, is a medium rich with structure. This view has deep philosophical implications. It challenges the ancient idea that nothing is truly nothing. For Feynman, emptiness was not a void waiting to be filled, but an essential part of how nature works. The vacuum is the ground state of fields, full of potential. From this potential, particles can appear, forces can act, and complex structures can emerge. Feynman's approach was also deeply honest. He did not pretend that these ideas were easy to visualize or fully intuitive. In fact, he often emphasized how strange they are. But he believed that accepting this strangeness was better than clinging to comforting but incorrect pictures. Emptiness being active is not just a poetic idea. It is a conclusion forced on us by experiments and mathematics. Modern physics continues to confirm Feynman's insight. Effects like vacuum fluctuations, particle interactions, and even theories about the expansion of the universe all rely on the idea that empty space has energy and structure. What once seemed like philosophical speculation is now central to our best scientific theories. In the end, Feynman's view connects emptiness with activity by showing that space itself is a participant in the universe, not merely a backdrop. Empty space is alive with fields, fluctuations, and interactions that shape everything we observe. Matter, forces, and even light depend on this hidden activity. What we call emptiness is not the absence of reality, but one of its most important and dynamic forms. The statement that nothingness in physics is full of structure sounds like a contradiction, but it captures one of the deepest insights of modern science. In everyday language, nothingness means complete absence. No matter, no energy, no motion, no influence. An empty room, outer space, or a vacuum seems like the closest thing to nothing we can imagine. However, when physics examines emptiness at a fundamental level, it discovers that what we call nothing is not empty at all. Instead, it is rich with organization, laws, and hidden activity. Classical physics once treated space as a passive stage. Objects moved through it, forces acted across it, but space itself did nothing. If all matter were removed from a region, what remained was thought to be pure emptiness. This view worked well for many everyday situations, but it began to break down as scientists explored the microscopic world. Experiments and theories revealed that space itself has properties, and these properties do not disappear when matter is removed. One of the first hints that nothingness has structure comes from fields. In modern physics, fields are fundamental. An electric field, a magnetic field, and more generally quantum fields exist throughout space. These fields do not require particles to be present in order to exist. Even in a perfect vacuum, where no atoms or particles remain, the fields are still there. They define how particles would behave if they appeared, and they carry energy and influence across space. Quantum field theory takes this idea even further. According to this framework, every type of particle corresponds to a field that exists everywhere in the universe. Electrons, quarks, and photons are not basic objects moving through empty space. They are excitations of underlying fields. When no particles are present, the fields remain in their low energy state, often called the vacuum state. This vacuum is what we usually mean by nothingness in physics, yet it is far from empty. A key reason nothingness has structure is the uncertainty principle. Quantum mechanics forbids perfect stillness. Even in the lowest energy state, fields cannot have exactly zero energy everywhere. As a result, they fluctuate constantly. Energy briefly appears and disappears, creating tiny disturbances in the fields. These fluctuations are not random noise without meaning. They follow precise mathematical rules and produce measurable effects. The vacuum is restless, not calm. These fluctuations are often described in terms of virtual particles. Virtual particles are temporary excitations that arise from quantum fields and vanish almost immediately. They cannot be directly observed, but their influence is real. They affect how forces act, how particles interact, and how energy is distributed. The fact that such activity occurs in empty space shows that nothingness has an internal structure governed by physical laws. Experiments confirm this structured nature of nothingness. One famous example is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience an attractive force. This force does not come from matter or classical forces. It arises because the structure of the vacuum changes between the plates. The allowed fluctuations of the fields are different in the small gap than in open space, producing a measurable force. Empty space, by itself, is doing something. Another example comes from atomic physics. The energy levels of electrons in atoms are slightly shifted by interactions with vacuum fluctuations. These shifts have been measured with extraordinary precision and match theoretical predictions. If nothingness were truly empty, these effects would not exist. The fact that they do exist tells us that the vacuum has a detailed and consistent structure. Nothingness is also structured by symmetry and laws. The vacuum is not just filled with random activity. It obeys deep principles such as conservation laws and symmetries of space and time. These symmetries determine what kinds of particles can exist, how forces behave, and how interactions occur. In this sense, the vacuum encodes the rules of the universe. It is like a background pattern that shapes everything built upon it. Richard Feynman and other physicists emphasized that this structured vacuum is essential for understanding reality. The forces that hold matter together operate through space, not across a void. The stability of atoms, the transmission of light, and the behavior of particles all depend on what space itself allows and supports. Nothingness is not the absence of physics. It is where physics begins. On the largest scales, the structure of nothingness may even influence the fate of the universe. Some theories suggest that the energy of the vacuum contributes to the expansion of space itself. This idea is connected to dark energy, one of the biggest mysteries in modern cosmology. Once again, what appears to be nothing may be shaping everything. This view challenges our everyday intuition. We are used to thinking that reality consists of things, and that empty space is just the gap between them. Physics suggests the opposite. Fields and space are fundamental, and what we call things are patterns within them. Nothingness is not a blank canvas, but a complex foundation with rules, activity, and potential. In the end, saying that nothingness in physics is full of structure means that absence of matter does not mean absence of reality. Empty space is filled with fields, fluctuations, symmetries, and energy. It plays an active role in shaping matter, forces, and the universe itself. What once seemed like pure emptiness is now understood as one of the most important and richly structured aspects of nature.